Welcome to Late Night History. Tonight, there is nowhere you need to be and nothing you need to do. You can let your shoulders drop. You can let the weight of the day go soft and loose, the way a held breath finally lets itself out. Wherever you are, however the hours behind you went, this hour is yours, and it asks nothing of you except that you stay a little while and listen. I want to tell you a story about a small, ugly, brown diamond. It was about 3 millimeters across. You could have set it on the tip of your finger and barely felt it there. It was the kind of stone that by every measure the world usually cares about was worth almost nothing. Cloudy, flawed, the wrong color, the sort of diamond that a jeweler would push to one side and a buyer would walk past without a second glance. No one was going to set it in a ring. No one was going to slide it into a velvet box. It was, in the plainest commercial terms, a piece of carbon that the trade had no use for. It cost about $20. Hold that in your mind for a moment, gently, the way you'd hold something fragile you were afraid to wake. $20. A small brown stone, no bigger than a grain of rice, that nobody wanted. And inside it, sealed away where no eye could see, was a secret about our planet so strange and so vast that when it was finally understood, it would force scientists to rewrite part of what they thought they knew about the inside of the Earth. The diamond came from a place called Juína, in the state of Mato Grosso, deep in the interior of Brazil. It is a region of rivers and red earth and old rock, a place where diamonds have been pulled from the ground and the riverbeds for a very long time. Most of those diamonds are like the one in our story, small, brown, ordinary. The miners and the traders sort through thousands of them, and the ones that aren't beautiful enough to sell as gems are gathered up and sold cheaply, by the handful almost, for whatever they might be worth. And it was out of one of those forgettable handfuls that this particular stone came, bought for a modest sum, brought into a laboratory not because anyone suspected it was special, but precisely because it was not. That is the first, quiet, strange thing about this story, and I'd like you to settle into it slowly because the whole night unfolds from here. The proof of one of the most extraordinary things ever discovered about our planet did not arrive on a beautiful diamond worth a fortune. It did not arrive in something rare and gleaming and prized. It arrived in a flaw. It arrived in the very thing that made the diamond worthless. Because what made that brown stone ugly to a jeweler was a tiny imperfection trapped inside it, a microscopic speck of something else, a little inclusion locked in the carbon. To a gem cutter, that inclusion was a defect, a reason to throw the stone away. To science, it would turn out to be a message in a bottle from 400 miles beneath our feet. The inclusion was smaller than the width of a single human hair. Think about that. Look, if you can, at one of your own hairs, or simply picture it, that fine, almost invisible thread. The thing that held the secret was smaller than its width, a speck within a speck. So small that it could barely be seen, even under the instruments built to see such things. So small that when scientists finally went to study it, they very nearly destroyed it in the act of looking. We will come to that. For now, just let the scale of it sit with you. The whole story, the entire revelation, was carried in something almost too small to exist in any way that matters to the human eye. And nobody knew what it was. That is the heart of where we begin tonight. Nobody knew what it was. A tiny grain of mineral trapped inside a cheap brown diamond from Brazil, and no one had ever held its like before, not from inside the earth. There was a name for the substance, a name that scientists had used for decades, but it was a name for something they had only ever predicted, only ever made in the laboratory under enormous pressure, or found in the wreckage of meteorites that had been born in violence out in space. Never once in all the years of geology had anyone held a piece of it that came from the depths of our own planet. It was a mineral that, as far as the surface of the Earth was concerned, did not exist. It could not survive up here. The conditions that make it are so extreme, so far removed from the gentle air and ordinary pressure of the world we live in, that it should fall apart the moment it rises into the realm of human beings. And yet there it was, held safe inside a diamond, carried up from the deep. So before we go any further, let me give you a sense of where this little grain of mineral had been. Let me give you the depth, because the depth is where the wonder of this begins to take hold. The mineral came from about 400 miles down. Now 400 miles is a number, and numbers can slide past you when you're tired. So let me slow it down and make it real. 400 miles. If you could drive straight down into the earth at highway speed, it would take you the better part of a long afternoon to reach the place this little grain came from. It is far below the deepest mine, far below the deepest cave, far below anything a human being has ever physically reached or ever could reach with the technology we have. It is below the crust entirely, below the thin skin of rock we live our whole lives upon, down into the great hot interior of the planet, into a layer we call the mantle. To understand just how unreachable that is, let me tell you about the deepest hole that human beings have ever drilled into the earth. It was a project in the far north of what was then the Soviet Union, on the Kola Peninsula, and it became known as the Kola Super Deep Borehole. For years, engineers and scientists drilled and drilled, pushing a slender shaft downward into the planet, deeper than anyone had ever gone, fighting heat and pressure and the simple, stubborn resistance of the rock. They drilled for about 2 decades. And, after all of that effort, all of that engineering, the very deepest they ever managed to reach was around 12 kilometers, about 7.5 miles. 7.5 miles. That is the deepest hole humanity has ever made. The greatest descent we have ever achieved into our own planet, the absolute furthest reach of all our machines and all our ambition. And the little grain of mineral inside that brown diamond came from 400 miles down. Sit with that for a moment, slowly. The deepest we have ever gone is 7.5 miles. This came from 400. That is deeper than our deepest reach by a factor of around 50. 50 times deeper than the furthest we have ever drilled. If our deepest borehole were the length of your arm, the place this mineral came from would be far, far across the room, out of sight, beyond anything you could touch. We cannot go there. We will likely never go there. The pressure would crush any machine we could build. The heat would unmake it. That depth is, for all practical purposes, as out of reach to us as the surface of a distant star. And that raises one of the quiet questions we will carry with us through this night. A loose thread to hold loosely as you drift. If we cannot go there, if the deepest we have ever drilled is 50 times shallower than the place this came from, then how on earth did a sample from 400 miles down ever reach the hands of a scientist? How did something from a place we can never visit end up sealed inside a cheap, brown diamond in a laboratory? That is part of what the night will slowly answer. Let it rest at the back of your mind. There is no hurry to know. Before we descend any deeper into the story, I want to do one small, warm thing, the way we always do here. I would love to know where in the world you are listening from tonight. Whatever the hour is where you are, whatever the weather is doing outside your window, leave a little note in the comments and tell me where you've drifted off from. It's a quiet pleasure on a subject as vast and as lonely as the inside of the earth to know that there are people scattered all across the world in different cities and different darknesses, all listening to the same slow story at the same time. And if you're new here, if this is the first of these you've found, you might want to subscribe so that the next slow story finds its way to you whenever you need somewhere calm to rest. And that is really all I want from you tonight, just to rest. You don't have to follow every thread. You don't have to remember the names or the numbers. If you fall asleep before the end, that is not a failure. That is exactly the point. I am going to lead you slowly, very slowly, down into one of the strangest discoveries ever made about our planet. And you are welcome to drift off anywhere along the way. The deep earth will keep. It has kept for billions of years. It can certainly wait for you to wake. So let us go down gently together. Now here is where I have to be honest with you, because the honest version of this story is so much stranger and so much more beautiful than the version you may have heard. And the version you may have heard goes something like this. You may have seen a headline somewhere, sometime, that said scientists had discovered a vast ocean hidden deep inside the Earth. An ocean bigger than all the oceans on the surface combined. A hidden sea locked away beneath the crust, a great dark body of water sloshing in the depths beneath our feet. It is a wonderful image, it really is. There is something in us that thrills to it, the idea of a secret sea. An undiscovered ocean, a hidden world of water down in the dark where the sun has never reached and never will. We picture caverns, we picture a black, still surface stretching away into nothing, an underground sea you might sail across, if only you could find your way down to its shore. We picture, perhaps, something out of an old adventure story, the explorers descending into the earth and finding water there, vast and cold and ancient. I have to gently take that picture away from you, because it is not true. There is no cavern, there is no hidden sea, there is no dark surface to sail across, no black water sloshing in some great hollow beneath the crust. If you went down to 400 miles deep, if somehow you could survive the heat and the pressure, you would not find an ocean, you would find rock. Solid, dense, hot rock, packed under such enormous pressure that there are no caverns at all, no hollows, no open spaces where water could pool. The popular image, the underground sea, the hidden ocean you could swim in, is a half-truth. It is the kind of half-truth that gets repeated until everyone believes it, the kind that fits neatly into a headline and a daydream. But here is the thing, and this is the turn. This is where I ask you to lean in just slightly before you let yourself go soft again. The truth, the real truth, is stranger than the myth. The real truth is more wonderful than the underground sea, because there is water down there, an astonishing amount of water. The discovery was real, the wonder was real, the water is genuinely, truly there. It is just not water the way you have ever imagined water. The water down there has, in a sense, stopped being water. Let me say that again, slowly, because it is the whole key to the night, the doorway we will walk through and then walk deeper and deeper beyond. The water down there has stopped being water. It is not liquid. It is not a puddle, not a pool, not a sea. You could not pour it. You could not drink it. You could not feel it as wet. And yet it is, by any reasonable accounting, water, more water perhaps than all the oceans of the surface put together. How can both of those things be true? How can there be more water than all our oceans, and yet no ocean at all, no liquid, nothing you could ever swim in or sip? Let me show you slowly the way you'd unfold something delicate. To understand it, I want you to think about water in a way you may never have thought about it before. We think of water as the thing in our glass, the thing in the sea, the thing falling from the sky, liquid, flowing, splashing. But water is also, at its smallest, a very simple little structure. It is made of atoms, 2 atoms of hydrogen, 1 atom of oxygen, joined together in that famous little arrangement we learn as children. That little 3-atom unit is the building block, the smallest possible piece of everything we call water. Now, in the ocean, in your glass, in the rain, those little units are loose. They tumble over one another, they slide and roll and flow, billions upon billions of them, free to move, free to pour, free to soak into the ground or rise into the air. That freedom, that loose, tumbling motion, That is what makes water a liquid. That is what makes it wet. That is what lets it slosh in a sea or run through your fingers. But there is another way for water to exist. Imagine, instead of those little units tumbling loose and free, that they were caught. Imagine that each one was taken apart, just slightly, and tucked carefully into a fixed place inside something solid, locked into position, held fast, no longer free to tumble or flow at all, not loose anymore, not liquid anymore, bound, built in, part of the structure of something else. That is what is happening 400 miles down. The water there is not free. It has been taken into the very architecture of the rock itself. To be precise, it isn't even whole little water units down there. The water has been broken into a slightly different form, a piece of itself, an arrangement called hydroxyl. It is one atom of oxygen joined to one atom of hydrogen, a fragment of water, half a breath of it, and that fragment has been built directly into the crystal structure of the minerals that make up the deep earth. Let me give you a way to picture that, because it is a hard thing to hold in the mind, and I want it to settle easily. Think of a crystal, any crystal, as a kind of building. Not a building of bricks, but a building of atoms, stacked in a perfectly regular repeating pattern, an invisible scaffolding of tiny pieces locked into a precise three-dimensional lattice, row upon row, layer upon layer, all in beautiful order. That ordered scaffolding is what makes a crystal a crystal. Now imagine that here and there throughout that scaffolding, in the small spaces and the joints of the structure, little fragments of water, those hydroxyl pieces, have been tucked in and bonded into place, woven right into the lattice of the rock. They are part of the building now. They are not water pooling in the basement. They are water built into the walls. That is the hidden ocean, not a sea in a cavern, water dissolved into stone, water that has become part of the rock itself, locked, atom by atom, into the crystal lattice of minerals so deep in the earth that they only exist under the crushing weight of the world above them. And once you understand that, once that picture settles, something rather lovely happens. The disappointment you might have felt when I took away the underground sea, the cavern, the dark water to sail across, that disappointment turns into something better, because an underground lake is just a lake that happens to be underground. We have those. They are not so strange. But water that has stopped being water, water dissolved into the atomic structure of crystals that cannot even exist on the surface, water hidden inside the architecture of stone 400 miles down, that is something else entirely. That is genuinely, deeply strange. And that is the kind of thing the universe does when no one is watching, the kind of secret a planet can keep for billions of years. And it is hiding, in the most literal sense, in plain sight. Not in a hollow, not in a cave, not in some empty space waiting to be found. It is hidden inside solidity itself, inside the very rock woven into the order of crystals. You could hold a piece of that deep rock in your hand if you could ever get it and if it could survive the journey, and you would not see water, you would see stone, and yet the water would be there, all through it, locked into the lattice, more of it by far than you would ever guess. This is why the proof of it was so hard to get, and why it took something as unlikely as a worthless brown diamond to deliver it. You cannot send a bucket down to fetch this water. There is no surface to dip the bucket into. You cannot drill to it, because the deepest we have ever drilled is 50 times too shallow. You cannot melt your way down, or dig your way down, or sail your way down. The water is locked inside minerals that only form under pressures we cannot reach, and those minerals brought up to the surface fall apart, change their shape, lose their structure, becoming ordinary rock, and giving up their secret on the way. The mineral that holds the water cannot survive the journey to us. Except just once it did, sealed inside the one thing on Earth hard enough and tight enough to protect it. sealed inside a diamond. And here is the quiet beauty of that, the symmetry that I find myself returning to whenever I think about this story. The thing that protected the secret, the diamond, is the same kind of thing the secret was hidden in, a crystal. A diamond is itself a crystal, a perfect lattice of carbon atoms, the hardest natural thing we know. It formed in the deep under enormous pressure, and as it formed, it happened to wrap itself around a tiny grain of that water-bearing mineral and seal it inside, the way amber wraps and seals an insect for 100 million years. The diamond became a sealed vault, a tiny pressurized capsule carrying its fragile passenger up and up and up through hundreds of miles of rock, all the way to the surface of Brazil, all the way to a riverbed, all the way to a handful of worthless brown stones sold for almost nothing. A vault built of crystal, carrying a secret made of crystal, holding water that had forgotten how to be water, up from a depth no human will ever reach. Now you can begin to feel, I hope, why this little brown stone matters so much, why the flaw inside it, the imperfection that made it worthless, was in fact the most valuable thing about it. The whole story, 400 miles of depth, a hidden ocean's worth of water, a discovery that would change part of what we understand about the inside of our world, all of it rode up to the surface inside a 3-millimeter diamond that cost about $20, in a grain smaller than the width of a hair, in a mineral no one had ever held before, in water that wasn't water at all. And nobody knew. For a while, even after the stone was in a laboratory, nobody knew what it held. It looked like nothing. It was nothing by every ordinary measure. The secret was so small, so well hidden, so far outside what anyone expected, that it could easily have been missed entirely. The diamond passed over, the inclusion ignored, the whole revelation lost back into the anonymity of all those countless brown stones from Juína. It was, in a very real way, an accident waiting to be noticed, a message in a bottle that had washed up on the shore and might just as easily have stayed buried in the sand. But it was noticed. Someone did look. Someone took that worthless little stone and turned their instruments on the tiny flaw inside it. And what they found when they finally understood it was the first piece of physical proof held in human hands of water locked inside the deep earth. The first actual sample, not a prediction, not a meteorite from space, not a laboratory imitation, but the real thing brought up from inside our own planet, of a mineral that proved the hidden ocean was real. We will come slowly to who that someone was, and to the strange, almost accidental way the discovery happened, and to how close it came to being destroyed before anyone understood what it was. We will come to the names of the minerals and the people who predicted them decades before anyone held one, and to the astonishing question of just how much water might be down there, woven into the rock, oceans upon oceans of it, none of it free, none of it liquid, all of it hidden in stone. We will come, in time, to the slow planetary cycle that carries water down into the deep and back up again over millions and millions of years, a cycle so slow that no human lifetime could ever watch it turn, linking the seas you have swum in to the hidden water 400 miles below. But none of that is for right now. Right now, I only want you to hold the picture we have built tonight, and to let it carry you towards sleep. A small brown diamond, 3 millimeters across, worth about $20, from Juína in Brazil. Inside it, a grain smaller than a hair. Inside that grain, water that has stopped being water, locked atom by atom into the lattice of a crystal that should not exist up here at all. And 400 miles below your resting body, below the floor, below the foundations, below the deepest hole humanity has ever drilled by a factor of 50, there is rock, hot and dense and packed under unimaginable pressure, and woven all through it, more water perhaps than fills every ocean on the surface of the world, held silent and still and bound into stone, where it has waited untouched and unseen for longer than there have been eyes to look for it. There is no cavern down there. There is no dark sea to sail. There is something stranger and quieter than that. There is water hiding inside the very bones of the planet, in plain sight and utterly invisible, and it has been hiding there all your life, all your grandparents' lives, all the lives of everyone who has ever lived, holding its secret patiently, far beneath the noise and the hurry of the surface world. And the first proof of it came up in a stone that nobody wanted. Let that settle now. Let the depth hold you, the way deep water holds a swimmer who finally stops fighting and simply floats. 400 miles down, the rock is still. The pressure is steady. The hidden water is bound and quiet and is going nowhere at all. There is nothing there to fear and nothing there that needs you. It is simply old and vast and calm, and it has kept its secret far longer than any of us will live, and it will keep keeping it long after this night has gone. Down in Juína, the rivers run over the red earth in the dark, carrying their ordinary brown stones the way they have for ages, none of them knowing what any one of them might hold. Somewhere, in a quiet laboratory, far from here, a worthless little diamond once gave up the strangest secret of the deep earth, and the world is a little more wondrous for it, though most of the world is sleeping and does not know. And further down, far below all of that, far below the deepest reach of any drill, the great hot mantle of the planet holds its hidden water close, locked into crystal, oceans of it dissolved into stone, still and patient and utterly out of reach. We are going down there, you and I, slowly, through the layers, through the depth, through the strange physics of pressure that can take water apart and tuck it into rock. We are going to follow that little brown diamond back down to where it came from, and we are going to understand gently and without any hurry at all how the hidden ocean came to be, and what it means that it is there, but not yet. Not all at once, for now there is only the depth and the dark and the quiet weight of the world holding its oldest secret, and your own slow breathing, easing further toward rest with every word. So let your thoughts grow as still as the deep rock. Let the surface noise fade, the way light fades the moment you slip below it. 400 miles is a long way down, and we have all night to travel it together. And there is nothing you need to carry with you. The diamond will wait. The water will wait. It has waited so very long already. Just breathe and drift and let the deep earth hold you for a while. The discovery itself began not with a grand expedition or a purpose-built instrument, but with a purchase so modest it barely registered in a research budget. Graham Pearson, a geologist at the University of Alberta in Canada, and the team working alongside him had acquired a small brown diamond from Juína in the Brazilian state of Mato Grosso. The stone cost somewhere in the region of $20 American. It was not pretty. It was not the kind of diamond that appears in the glass cases of jewelers or catches light in any way that draws the eye. It was dull, inclusions visible within it, the sort of diamond the trade has always set aside as commercially worthless, fit for industrial grinding wheels or abrasives, not for any finger or throat. Nobody walking past it would have paused, nobody handling it would have felt they were holding anything remarkable. But inside it, sealed as neatly as a letter inside an envelope, something had been waiting for a very long time. The team had not set out looking for what they found. That is perhaps the most important sentence in this whole story, and it is worth holding for a moment. Science runs on intention, on hypotheses and instruments trained toward a specific question. But some of the deepest discoveries come sideways, from the peripheral vision of a careful eye. Pearson's group had acquired the diamond with a different purpose in mind entirely. They wanted to date the stone to establish when it had formed in the deep earth, using the chemistry of another mineral they hoped to find inside it. That other mineral was the target. The dating was the goal. What they discovered instead was not the thing they were looking for. The diamond was approximately 3 millimeters across. That is roughly the diameter of a pencil's worth of graphite, the grey core you'd press into a page, small enough to hold between 2 fingers without much thought. And within that small brown stone, a microscopic inclusion, a speck of something other, caught the team's attention. The inclusion was so small it measured less than the width of a single human hair. Less than the width of a single human hair, and yet what it contained would require a revision of how geologists thought about the deep interior of the planet. Nearly destroyed first. The analysis very nearly consumed the inclusion entirely before its nature and water content could be confirmed. That is a detail worth sitting with for a moment. How close the whole discovery came to not happening. How the evidence for an ocean buried in rock inside the earth almost dissolved on the instrument before anyone could read it. The margin between knowing and not knowing was that thin. There is something in that which speaks to how much we almost miss, how many secrets the deep earth has already swallowed whole, dissolved back into ordinary seeming rock before the light could reach them. But the inclusion survived, just barely, and what Pearson's team identified inside it changed the science. The mineral was ringwoodite. That name is not one most people carry with them, and it does not need to be spoken quickly. Ringwoodite. It is named for a man which we will return to. And what it is chemically requires a short bridge to understand. Not a difficult bridge, but a necessary one. Deep within the upper mantle, at depths you and I spend our whole lives above, the dominant rock-forming mineral is olivine. If you have ever seen a pale greenish-yellow stone in a geological collection, rough-hewn and glassy, you may have seen olivine or a gem-quality version of it called peridot. The upper mantle, the enormous hot rocky layer beneath Earth's thin outer crust, is largely composed of it. Olivine is, in a sense, the ordinary rock of the deep. Magnesium, iron, silicon, oxygen, arranged in a crystal structure that is stable under the pressures that exist from just below the crust down to somewhere around 410 kilometers depth. But pressure is not constant through the Earth. Pressure increases as you go down, and at a certain depth it becomes so immense that olivine cannot hold its shape. The atoms are squeezed into a tighter arrangement. The crystal structure collapses inward and rebuilds itself in a new configuration, denser and different, but made of the same atoms. The chemical formula does not change. What changes is the architecture. Imagine a building made of the same bricks, rearranged from a low, spread-out structure into something taller and more compact because the space has shrunk around it. The bricks are the same, the building is not. At roughly 525 kilometers depth, olivine reorganizes itself into wadsleyite, and then again at approximately 525 to 660 kilometers depth, it rearranges once more into ringwoodite, a higher pressure form still, denser again, smaller atomic spacing, tighter lattice, a crystal structure adapted to conditions so extreme that reproducing them in a laboratory requires specialized equipment pressing samples between diamonds, generating pressures that exist nowhere on the surface of this planet. Ringwoodite is, then, a high-pressure version of olivine. Geologists call it a polymorph, meaning same composition, different crystal form. It is stable in the lower part of what geologists call the mantle transition zone, that layer of the Earth from 410 kilometers depth down to 660 kilometers. Below 660 kilometers, the pressure crosses another threshold, and ringwoodite gives way to yet denser minerals of the lower mantle. Above 410 kilometers, the pressure is not quite high enough to sustain it, and olivine is what you get instead. So ringwoodite belongs to a very specific window of depth. It is the rock of a particular zone, the way certain trees belong to a particular band of altitude on a mountain. Below the tree line you get forests, above it you get bare rock. Ringwoodite lives in its own band, between the seismic discontinuities that mark where one mineral world ends and another begins. And the remarkable thing about ringwoodite, the thing that sets it apart from ordinary olivine and gives it its role in the story of the hidden ocean, is this. When it forms under those extreme pressures, it can take water into its crystal structure in a way that ordinary olivine cannot. The tighter atomic architecture of ringwoodite creates, in effect, spaces within the lattice where hydroxyl groups, that is, one oxygen atom bonded to one hydrogen atom, written as OH, can sit and be held not as liquid water, not as ice, but as a chemical part of the mineral itself. Water dissolved into stone. Atoms of hydrogen tucked so deeply into the crystal architecture that they are not, in any ordinary sense, water anymore. They are part of the rock. And in the inclusion inside that small brown Brazilian diamond, the ringwoodite that Pearson's team identified contained approximately 1.5% water by weight. 1.5% does not sound like much, but consider the scale. If the mantle transition zone, that band from 410 to 660 kilometers depth, was saturated with ringwoodite and wadsleyite holding water at those concentrations, the total volume of water locked within it could equal 1 to several times the combined volume of every ocean on Earth's surface. All of the Pacific, all of the Atlantic, the Indian, the Arctic, the Southern, matched or exceeded by water that exists not as liquid, not as any kind of sea you could imagine, but dissolved into the atomic fabric of deep rock, silent and motionless and incalculably old. That is what was sitting in that $20 stone. The study was published in the journal Nature in March 2014. The lead author was Graham Pearson, the paper reporting the first confirmed natural terrestrial sample of ringwoodite ever recovered from Earth's own interior. The word terrestrial is important there. Ringwoodite had been known to science before this. It had been found in meteorites and rocks that fell from space where the tremendous pressures of ancient asteroid impacts briefly replicated the conditions of the deep Earth and forced olivine into that tighter crystal form. Scientists had known for decades that ringwoodite could exist in theory and had confirmed it could exist in extraterrestrial rock. But to hold a piece of Earth's own ringwoodite, sourced unambiguously from Earth's own mantle transition zone, had never been done. Every piece of evidence for the mineral's presence in the deep Earth had been indirect, inferred from seismic data, simulated in laboratory experiments, theorized from physics. The diamond from Juína was the first direct physical proof. A sample, however microscopic, from the place itself. Why a diamond, specifically? That question matters, and the answer to it is one of the most quietly extraordinary details in this whole story. Consider the problem you face when you wish to study a mineral that exists at 500 or 600 kilometers depth. The deepest borehole humans have ever drilled is the Kola super-deep borehole in what was the Soviet Union, a project that ran for decades and reached approximately 12 kilometers into the Earth's crust. 12 kilometers. 600 kilometers is 50 times deeper. The Kola borehole, for all its extraordinary engineering, barely punctured the skin of the planet. At 12 kilometers, the temperatures and pressures were already sufficient to make further drilling essentially impossible with any technology that existed. The rock behaved almost like plastic at that depth, flowing slowly toward the drill, closing back in behind it. At 400 miles down in the mantle transition zone, the pressures are approximately 200,000 times the atmospheric pressure at Earth's surface. The temperature sits somewhere between roughly 1400 and 1800 degrees Celsius, No drill, no instrument, no human technology has ever come close to reaching that depth, and none that exists today could. The deep mantle is more inaccessible to us than the surface of Mars, in a very real sense. Mars we have landed probes on. The deep mantle we have only ever touched through inference and mathematics. And yet, here was a piece of it, sitting in a tray in a laboratory in Canada. The reason is diamond. Diamond is the hardest naturally occurring substance on Earth. Its carbon atoms are arranged in an exceptionally strong crystal lattice, a structure so robust it can survive pressures and temperatures that would destroy almost any other material. Diamonds form in the mantle, typically at depths between roughly 100 and 250 kilometers, in the lithospheric mantle beneath old, stable continental crust. They grow slowly over geological timescales, encasing small amounts of surrounding rock or mineral as inclusions within their growing structure. And because diamond is so exceptionally rigid, so resistant to chemical exchange with its surroundings, it acts as a sealed chamber. Whatever is locked inside a diamond at the moment of its formation stays locked inside, preserved at the pressure and temperature and chemical conditions of that depth for as long as the diamond remains intact. It is a natural vault grown in the dark, millions or hundreds of millions or even billions of years old in some cases, carrying its contents to the surface without alteration. The diamond from Juína is believed to have originated from considerably greater depth than most diamonds, potentially from within or near the mantle transition zone itself, which is why it contained a mineral stable only at those pressures. It is a so-called superdeep diamond, a category of stone that forms below the normal lithospheric diamond stability field within the deeper mantle where the pressures are sufficient to maintain ringwoodite and other transition zone minerals. The inclusion of ringwoodite inside it is evidence of where the diamond spent its formation, the way a postmark on an envelope tells you something about the journey before arrival. And the ringwoodite itself, once enclosed within that diamond, was protected from the journey upward. Here is the thing: minerals that are stable at high pressure become unstable when pressure drops. Olivine, the low-pressure form, is stable near the surface. Ringwoodite, the high-pressure form, is not stable near the surface. If a piece of ringwoodite were exposed to surface conditions, if it were brought up slowly in a normal rock without any protective casing, it would transform back into olivine. The pressure relaxes, the atomic structure rearranges, and the ringwoodite ceases to be ringwoodite. This is why no one had found it before. Every piece of mantle transition zone material that arrived at the surface through ordinary geological processes had converted back into the lower pressure forms along the way. The evidence erased itself in transit. The diamond prevented that. The rigid walls of the carbon lattice kept the inclusion sealed under something approximating the conditions of the deep interior, even as the diamond was carried upward and the pressure outside changed dramatically. The ringwoodite inside the diamond, shielded from the outside world, remained ringwoodite. The vault held, and that vault arrived at the surface through an eruption unlike most volcanic events in terms of speed and depth of origin. Ordinary volcanoes draw their magma from the upper mantle or lower crust, depths of perhaps tens of kilometers. A kimberlite eruption is different. Kimberlites are a type of igneous rock formed from magma that originates in the deep mantle at depths of at least 150 kilometers, sometimes considerably more. The eruptions that bring kimberlite to the surface are notably fast as geological processes go, which is not fast by any human measure, but fast enough to matter. The magma ascends through the mantle and crust in what geologists describe as a relatively rapid passage, driven by volatile compounds, including carbon dioxide and water expanding as pressure drops, the whole column accelerating upward, carrying with it whatever xenoliths and inclusions it encounters on the way. Fast ascent means less time at intermediate pressures and temperatures. Less time at intermediate conditions means less opportunity for the minerals within the ascending material to re-equilibrate, to transform into the lower pressure phases they would otherwise become. The kimberlite eruption is, in effect, the only natural elevator on Earth capable of delivering material from the deep mantle to the surface before the evidence dissolves. It is narrow, it is violent on geological scales, it bores a roughly cylindrical pipe through the overlying rock, and the rocks left behind in those pipes, kimberlites, are among the most mineralogically remarkable on Earth because they carry fragments of the deep interior that no other process delivers intact. The region around Juína in Mato Grosso, Brazil, sits above an ancient set of kimberlite pipes that have been eroding and delivering their contents to river gravels for an enormously long time. Diamond miners and collectors have worked those gravels for decades. The diamonds found there include an unusual proportion of the super-deep variety, stones that carry evidence of origins in the lower mantle or transition zone. The diamond that Graham Pearson's team purchased, that small, dull, $20 brown stone, was one of those. It had been carried to the surface in a kimberlite eruption at some point in the geological past. The exact age of the eruption is not the critical fact here. And then, over the long, slow processes of weathering and erosion, it had been released from the kimberlite rock and concentrated in the river gravels along with other heavy minerals, where eventually it was collected and sold again until it reached a researcher who happened to know that diamonds like this one from this region sometimes carry contents more valuable than their gem grade. The inclusion inside it was studied using a technique called Raman spectroscopy, which identifies minerals by the way they scatter laser light, producing a spectral fingerprint as distinctive as a human face. The ringwoodite inside the Juína diamond has a specific spectral signature, measurable even from a fragment far smaller than a grain of sand, and that signature confirmed what it was. The hydroxyl groups within it, the chemical evidence of water bonded into the crystal, were also detectable spectrally. 1.5% water by weight, locked into the atomic architecture of a mineral that no longer exists anywhere on Earth's surface under natural conditions, preserved inside a diamond that should by rights have been worth only a few cents per carat, found almost by accident by a team that had been looking for something else entirely. There is a particular quality to this kind of scientific accident that is worth noting because it recurs in the history of discovery. The apparatus is aimed at one thing, and on the periphery of that aim, something else appears that is far stranger and more significant than the intended target. Pearson's team had wanted to date the diamond. The dating required finding an appropriate mineral inclusion from which radiometric ages could be extracted. Instead, they found ringwoodite. And inside the ringwoodite, water. The original goal, the dating, became a secondary matter. The accidental discovery rearranged the significance of everything else. The analysis nearly destroyed the inclusion too. That detail carries a weight that is difficult to fully articulate. The testing process required material from the inclusion itself, and the inclusion was so small that the analysis consumed most of it before the full picture could be confirmed. The researchers were working at the edge of what was technically possible with the instruments available. A slightly larger sample taken, a slightly different analytical approach, and there might have been nothing left to confirm. The discovery was made by a narrow margin. The evidence was balanced on a knife's edge for some time before the results were clear enough to mean anything certain. And when they were clear, when the spectral signature confirmed ringwoodite and the hydroxyl signal confirmed water, what the team had in hand was the first physical proof that the mantle transition zone of the Earth contains water, not as a theoretical inference, not as a laboratory simulation of what might happen under high pressure, but as a fact witnessed in an actual sample from the actual depth. The study, published in Nature in March 2014, made this claim carefully and precisely, as science tends to do with claims of this magnitude. Not that there is an ocean, not that there is a sea, that there is water as hydroxyl bonded into the structure of ringwoodite, and that the concentration of that water in this one sample is approximately 1.5% by weight, and that if similar concentrations hold throughout the transition zone, the implications for the total volume of water stored in the deep earth are very large indeed. That hedge, if similar concentrations hold, is not false modesty. It is the honest shape of the knowledge. One inclusion in one diamond is not a global census. It is a data point, an extraordinary one, a proof of existence, but not a measurement of totality. The extrapolation from that point to the estimate of one to several ocean volumes of stored water involves assumptions about how uniformly the transition zone is hydrated, how consistently ringwoodite and wadsleyite hold water at those concentrations throughout the whole vast zone, and those assumptions are informed by laboratory experiments and seismic inference, not by a comprehensive survey of the deep interior. The estimate is credible. It is the scientific community's best current reckoning, but it is not a census, and the researchers said so. That honesty is part of what makes the discovery more interesting, not less. If the answer were neat and certain, it would sit quietly in a textbook. The fact that it is real, confirmed but still bounded by uncertainty at the edges, still the subject of ongoing measurement and debate, means the question is alive. The deep earth is still giving up its secrets gradually, and this is one of the most extraordinary it has offered so far. What it means for water on Earth's surface and where the water in the transition zone came from is the next question the story opens. But even within the discovery itself, within the narrower frame of what Graham Pearson and his colleagues found and reported in 2014, there is already more strangeness than most geology contains in a decade. A stone worth $20, an inclusion smaller than a hair, a mineral named for a man who never held it in its terrestrial form, water that is not water, pressed into the architecture of a crystal by the weight of 400 miles of rock above it, and a volcanic pipe that fired all of it upward like a message in a bottle sent from a depth no one has ever visited, and no one is likely to visit in any foreseeable future. The diamond sat in a tray, the instrument read it, the data came back, and somewhere in a quiet office, someone looked at a spectrum on a screen and understood that they were looking at evidence of something no human being had ever directly examined before. The interior of the Earth, not as a diagram in a textbook, not as a color-coded cross-section on a classroom wall, but as a physical sample, an actual piece of it, small as a hair and full of ancient water, sitting in a laboratory in Canada under fluorescent light, entirely ordinary to anyone who did not know what it held. The question the discovery opens, the question that becomes the river the rest of this story flows down, is what it means that the water is there at all. Not just the fact of it, but the process. How did hydrogen and oxygen come to be buried at 400 miles depth, tucked into the atomic structure of rock, in quantities that may rival or exceed all of Earth's surface oceans? What mechanism carries water from the surface world of rain and rivers and seas down into the furnace of the deep mantle, and over what span of time? And what happens to the water once the rock that holds it sinks too deep for ringwoodite to survive? Those questions belong to the part of the story that runs from the surface down, from the cold grey surface of the ocean floor, where tectonic plates crawl at the speed of a fingernail growing, down and down through the crust and into the mantle, along the descending path of a subducting slab, through the slow transformation of minerals under increasing heat and pressure, all the way to the zone where ringwoodite begins to sweat. But before that, there is still something to understand about the two minerals at the center of this story, about the men whose names they carry, and about the remarkable fact that one of them was first discovered not in the earth at all, but in rocks that fell from the sky. Because ringwoodite, before it was found in a Brazilian diamond in the laboratory of Graham Pearson, was a mineral of meteorites and theoretical physics. It existed in the record of cosmic impacts and in the equations of researchers who had never touched a terrestrial sample. The story of how it came to be known and by whom is one of those quiet histories that sits behind the headline discovery, invisible unless you look, and worth the looking. The names on the minerals tell you where to start, and that is where we will go next, as the night deepens and the surface world grows quieter, and the dark above this room is the same dark that covers the river gravels of Mato Grosso, where the diamonds lie in the gravel, waiting, slow and patient, for whatever hand might next find them. Let the weight of that depth settle around you for a moment. 600 kilometers. The whole of the transition zone, from 410 kilometers down to 660, holding water that has nowhere to go and no way to escape, water that has been part of the rock for longer than the Atlantic Ocean has existed. The Atlantic is relatively young, geologically speaking. The water in the mantle transition zone may be older than any ocean that has ever spread across the surface of this planet. And the diamond brought it up. The kimberlite pipe fired it to the surface. The river moved it into the gravel. A miner lifted it out of the water. A collector bought it for almost nothing. A researcher bought it from a collector for almost nothing. And in a laboratory under a laser, the evidence finally became visible. Rest now in that image. The whole long chain of it, from the crushing dark of the deep mantle to a quiet laboratory. The water that waited inside the crystal all the way through that journey, unchanged, unspilled, pressed into the rock and carried like a secret that had been looking for someone to tell it to. The deep earth is patient in a way that nothing on the surface can match. It does not hurry. It does not announce itself. It waits, and occasionally a diamond arrives at the surface and tells us something we were not expecting to hear, something that changes the shape of what we thought we understood about the planet we live on. And tonight, in the dark, while the surface world sleeps, that story is still unfolding, and the water is still there, 400 miles below, locked in the mineral architecture of rock that has not seen light since before human beings existed, quiet and permanent and impossibly deep. There were two men who knew the minerals existed before anyone had ever held them in their hands. That is an unusual thing in science, to name something that has not yet been found, to describe its structure and its properties and its pressure range, and give it a place in the ordering of the world before it arrives to confirm what you have said about it. Most of science works the other way. You find the thing and then you figure out what it is. These two men worked in the opposite direction, and both of them turned out to be right. The first was an Australian geophysicist named Alfred Edward Ringwood, who was known to almost everyone as Ted. He was born in 1930 in Kew, a suburb of Melbourne, and he spent much of his career at the Australian National University in Canberra in the decades after the Second World War, in an era when geoscience was undergoing a quiet revolution. The theory of plate tectonics was still being assembled and argued over. The interiors of planets were almost entirely theoretical territory, reachable only through seismology and experiment, because no drill could get there and no instrument could be lowered down. Ted Ringwood worked in that territory as a matter of choice, because it was where the most important and least answered questions lived. He was interested in what happens to rock under pressure. Not ordinary pressure, not the pressure you feel if you dive to the bottom of a swimming pool or even the bottom of the sea, but the kind of pressure that builds when you move 50 kilometers down, 100, 200, 300, 400, the kind of pressure that does not compress rock so much as it rearranges rock atom by atom, forcing the constituent parts of minerals into new geometrical configurations that are denser, more tightly packed, structurally different from anything the same mineral becomes at the surface. He wanted to know what olivine became when it was pressed hard enough. Olivine is one of the most abundant minerals in the Earth's mantle. If you could somehow scoop up the material that makes up the great bulk of our planet's interior, a large fraction of what you held would be olivine or something derived from it. It is a magnesium-iron silicate, a greenish mineral common enough that it is semi-precious in its surface form, used in jewelry found in volcanic rocks collected from beaches on certain Hawaiian islands where the sand itself runs a faint olive green because it is made of the stuff. At the surface, under ordinary conditions, olivine is olivine. But Ringwood understood that deep in the mantle, under the weight of hundreds of kilometers of rock bearing down from above, olivine could not remain olivine. He predicted, through a combination of thermodynamic reasoning and high-pressure experimental work, that at the depths corresponding to roughly 410 kilometers below the surface, olivine would transform. The atoms would not change, the fundamental chemistry would remain the same, but the architecture of the crystal itself would collapse and rebuild into a new configuration, denser and more ordered, a kind of olivine that had never existed anywhere on the Earth's surface under natural conditions. He calculated what this new mineral would look like. He described its properties. He assigned it a place in the mineral kingdom before anyone had ever seen it. He was describing what we now call wadsleyite, and he predicted that at even greater depths, somewhere below roughly 525 kilometers, the transformation would happen again. The mineral would undergo a second reorganization, packing itself even more tightly under the even greater pressure of the deeper transition zone, producing a third form, a third architecture built from the same atoms as the original olivine, but structured differently from either its shallow cousin or its surface ancestor. This third form, the deepest and most compressed, would eventually bear his name. Ringwood published this work through the 1960s and into the 1970s. He built apparatus capable of generating some of the highest static pressures achievable in a laboratory at that time, multi-anvil presses and diamond anvil cells where two small gem-quality diamonds are pressed face-to-face with the sample trapped between their tips, squeezing a microscopic volume of material to pressures that mimic the interior of the Earth. In those machines, on a laboratory bench in Canberra, he and his colleagues watched olivine transform. They watched it become the new mineral he had predicted. They produced samples of what would come to be called wadsleyite and, at higher pressures still, what would come to be called ringwoodite. He held them in his hands, or at least held the instruments that contained them, minerals that existed naturally only in a place no human being has ever visited or ever will. He died in 1993, which means he did not live to see the 2014 discovery, the small brown diamond from Juína carrying ringwoodite from the actual mantle of the actual Earth. He knew the mineral in its laboratory form. He had predicted it, made it, described it. But the confirmation from the planet itself, the sample that said this is not only what we can create in an apparatus, this is what the Earth contains in its own body, 400 miles down. That confirmation came 21 years after he was gone. It arrived bearing his name. The second man was Arthur David Wadsley, a British-Australian mineralogist who worked at the Commonwealth Scientific and Industrial Research Organisation in Australia, known as the CSIRO, during roughly the same post-war era. Wadsley was a crystallographer, someone who studies the architecture of crystals, the way atoms arrange themselves in three-dimensional lattices that repeat, pattern after pattern, at a scale invisible to the human eye, but determinative of everything a mineral can do. He did not work specifically on high-pressure mineral phases, but his detailed structural work on oxides and related compounds provided foundational crystallographic techniques that the high-pressure community used and built upon. When the intermediate depth olivine polymorph was formally named, it was named for Wadsley, in recognition of his contributions to mineral crystallography. He died in 1969, and the mineral that carries his name would not be found in a natural terrestrial sample for decades more. Between them, these two men gave the mantle transition zone its vocabulary. The zone itself, the region between roughly 410 and 660 kilometers depth, had been recognized by seismologists for some time before either man completed his most important work. When you study the Earth with seismic waves, the vibrations generated by earthquakes and recorded at distant stations spread across the surface, you can read the interior of the planet the way a doctor reads an X-ray, not by seeing through it directly, but by watching how the waves change speed and direction as they travel through different materials. Seismologists had noticed, as early as the mid-20th century, that seismic waves changed their behavior abruptly at certain depths, accelerating or bending or reflecting in ways that indicated a sharp change in the material they were passing through. These sharp changes are called seismic discontinuities, and there are two major ones that define the transition zone. The first is at approximately 410 kilometers depth, where the waves speed up abruptly, indicating that the rock has suddenly become denser. This is the 410-kilometer discontinuity, and what is happening there is exactly what Ringwood's work described. Olivine is transforming into wadsleyite under the pressure of the overlying rock, shifting from one crystal architecture to a denser one, and the denser rock transmits seismic waves faster. The second discontinuity is at approximately 660 kilometers depth, where another abrupt change occurs, and where ringwoodite, the high-pressure form, stable between roughly 1525 and 1660 kilometers, can no longer survive the conditions below and transforms yet again into minerals characteristic of the lower mantle. Between these two boundaries lies the transition zone, a shell of rock 250 kilometers thick, wrapped around the entire planet, in which wadsleyite and then ringwoodite hold their shapes under pressures that would be incomprehensible to describe in everyday terms, except to say that the weight of everything above them would pulverize anything familiar. Wadsleyite occupies the upper portion of this zone from roughly 410 to 525 kilometers down. It is structurally similar to ringwoodite but not identical. The atoms of magnesium and iron and silicon and oxygen arranged in a slightly different configuration, slightly less densely packed than its deeper cousin. And here is where the story of water becomes, if possible, even stranger. Wadsleyite has a particular affinity for water. Its crystal structure, in laboratory experiments conducted under the high-pressure conditions that prevail in the upper transition zone, can accommodate a remarkable proportion of water by weight, up to approximately 3%. If you imagine a kilogram of wadsleyite at depth, 300 grams of that kilogram could, in principle, be water. Not liquid water occupying space alongside the mineral. Water that is part of the mineral itself, hydroxyl groups, the OH pairing of one oxygen and one hydrogen bonded into the crystal lattice, woven into the architecture of the stone. 3%. That number is larger than the 1.5% measured in the ringwoodite inclusion from the Brazilian diamond, and that difference tells you something about how the transition zone works as a water storage system. The shallower mineral holds more water per unit of rock. The deeper mineral holds somewhat less. Together, spread across the full depth of the zone, the two minerals create a vast reservoir that is neither liquid nor gaseous, nor anything that the surface world would recognize as water. And yet the water is demonstrably, chemically, measurably there. There is something worth pausing on in that number, 3% water by weight. Think for a moment about something you would call dry, a piece of quartz, a common mineral, clear and crystalline, sitting on a table. It looks dry, it feels dry, it is as dry as anything you can imagine. Nothing about it would lead you to suspect it contains water. The mantle transition zone minerals look no different from the outside. They are rock. They look like rock. But under the conditions of the deep earth, they are rock that has quietly, over millions of years, absorbed a fraction of the water that passed through or near them, bonding it into their crystal structure, in a form that the minerals carry as part of their own identity, not as a contaminant but as a constituent. The rock is wet in a sense that has no analogy at the surface, wet in its bones, wet in the geometry of its atoms. This is what Ted Ringwood and Arthur David Wadsley set in motion, the framework that made it possible to understand what the 2014 diamond was telling us. Without the prediction of these minerals, without the laboratory creation of them and the careful characterization of their properties, the tiny inclusion in that small brown stone from Mato Grosso would have been uninterpretable. It arrived bearing a message written in a language that had taken decades to develop, and the minerals had arrived in scientific consciousness from another direction first, from above, not from below. Before anyone found ringwoodite or wadsleyite in a sample from the Earth's own mantle, before the kimberlite pipes of Africa and Brazil and Canada spat up anything that carried these high-pressure phases intact, the minerals had been found somewhere altogether more dramatic. They had been found in meteorites. Meteorites are pieces of the early solar system that have survived the journey from space to the Earth's surface, and many of them bear the marks of ancient violence. In the billions of years since the solar system formed, rocks have collided with other rocks, sometimes at speeds and energies that defy easy imagination, impacts that briefly generate pressures comparable to those deep inside the Earth. When a meteorite strikes a planet or a large asteroid strikes something smaller, the shock wave propagating through the rock on impact can, in a fraction of a second, compress the minerals caught in it to mantle-like pressures. The event is over almost immediately. But in that brief window, the minerals can transform, just as they transform over millions of years in the slowly deepening mantle, and if the shocked rock then cools quickly enough, the new high-pressure phases can be frozen in place, preserved in the meteorite's matrix, waiting to be found. Ringwoodite was identified in meteorites decades before it was confirmed in any terrestrial sample from Earth's own interior. The name was applied to the meteoritic mineral in the late 1960s before any terrestrial ringwoodite had been described, because the identification was there in the shocked achondrite meteorites in the veins of altered olivine running through the broken rock, evidence of the pressure and the transformation built into the grain of the stone by the violence of an impact that happened long ago, somewhere in the inner solar system, on a body that no longer exists in the same form. There is something quiet and remarkable about that. The mineral that turned out to be a key to understanding the interior of our own planet was first described not from our planet at all. It arrived in our scientific vocabulary through the study of debris from somewhere else, through the careful peering at the composition of rocks that fell from the sky. The Earth's own ringwoodite, the ringwoodite that had formed under the slow, patient compression of the mantle, held inside a kimberlite diamond through the long ages, carried to the surface by an eruption, moved by a river, lifted by a miner, traded, and finally analyzed. That terrestrial sample had to wait until 2014 to be confirmed, decades after the mineral had already been named for something found in cosmic wreckage. It is one of the more quietly strange reversals in the history of geology. The lesson written inside the Earth was first read in the sky, but by 2014 the framework for reading it was complete. The laboratory work existed. The predictions had been made and confirmed experimentally. The mineralogical vocabulary was in place, and the question of whether the actual transition zone, the real zone deep inside the real Earth, rather than the simulated zone inside a high-pressure apparatus, actually contained water at the concentrations the laboratory experiment suggested, was still unanswered. Pearson's diamond gave one answer. A microscopic inclusion in one small stone confirmed that ringwoodite from the natural terrestrial mantle did contain water, roughly 1.5% by weight, and that therefore the transition zone was at least damp, at least partially hydrated, at least not dry in the way that older models had sometimes assumed. But one diamond is one diamond. One inclusion is one data point. Science does not usually overturn its assumptions on the basis of a single sample, however beautiful and however carefully analyzed. The question of whether the whole transition zone was wet, or only pockets of it, or whether the sample was anomalous, whether the Brazilian kimberlite had tapped an unusually hydrated region of the mantle that could not be generalized to the rest of the planet, remained genuinely open. The answer to that question came from a completely different direction. From above, from the surface, from sound. Stephen Jacobson is a mineralogist and geophysicist at Northwestern University in Evanston, Illinois. Brandon Schmant is a seismologist at the University of New Mexico in Albuquerque. In the same year that Pearson's team published their diamond result in Nature, Jacobson and Schmant published a separate study in Science, a different journal, a different approach, a different kind of evidence, arriving at a conclusion that pointed in the same direction. What Jacobson and Schmant did was listen to the planet. Earthquakes generate seismic waves, and those waves travel through the interior of the Earth in patterns that depend on the properties of the materials they pass through. The speed of a seismic wave is not fixed. It changes depending on the temperature of the rock it moves through, the pressure it is under, the composition of the mineral, and crucially, whether the material it is moving through is entirely solid or contains any partial melt, any fraction of material that is beginning to transition from solid to liquid under the conditions prevailing at that depth. Partially molten rock transmits certain kinds of seismic waves more slowly than fully solid rock. The change in speed is measurable, and a network of sensitive seismometers placed across a continent can, by recording the arrival times and amplitudes of seismic waves from earthquakes in different locations, build up a three-dimensional picture of the Earth's interior, a kind of geological tomography. The US Array was a network of seismic recording stations that had been deployed across the United States as part of a larger research initiative called EarthScope. At the time of Jacobson and Schmant's work, it comprised more than 400 individual stations spread across the continent, each one recording the ground motion generated by distant earthquakes with high precision. The network had the particular advantage of covering a large geographic area systematically, which meant that seismic waves arriving from earthquakes at different depths and different distances could be analyzed together, building up a picture of what lay beneath North America at various depths. Jacobson and Schmant used data from more than 500 earthquakes recorded across this network. They focused specifically on what the seismic waves were telling them about conditions near the 660-kilometer boundary, the lower edge of the mantle transition zone, the depth at which ringwoodite gives way to the minerals of the lower mantle. And they detected something. The waves showed evidence of slowing in places at the base of the transition zone, consistent with the presence of partial melt, not complete melting, not liquid rock in a vast pocket, but rock that was, in fractional microscopic terms, beginning to transition from solid to something that was not quite solid, a fraction of melt distributed through otherwise solid rock, the seismic equivalent of ice beginning to thaw at its edges while most of it remains frozen. This was not by itself unexpected. Partial melt can result from heat alone, and the lower mantle is extraordinarily hot. But Jacobson and Schmant had been doing laboratory experiments in parallel with the seismic work, experiments in which they subjected ringwoodite to the temperatures and pressures prevailing at approximately 660 kilometers depth, and then pushed those samples into the conditions of the uppermost lower mantle, the region just below the transition zone boundary. And what they found in the laboratory was consistent with what the seismic waves seemed to be showing. When ringwoodite crosses the 1660-kilometer discontinuity, when it descends into conditions where it can no longer maintain its high-pressure crystal structure, it transforms into the minerals of the lower mantle. And the water that was bonded into its structure, the hydroxyl groups that the crystal had been holding inside its lattice, is released. The mineral, in effect, sweats. The water that ringwoodite releases at 660 kilometers does not simply disappear. It enters the surrounding rock in a form that lowers the melting point of that rock. Water, even in small amounts, even as hydroxyl groups rather than as liquid, reduces the temperature at which silicate minerals begin to melt. This is a well-established principle in experimental petrology, the study of rocks and their behavior under heat and pressure. You add water to hot rock and you lower the melting point. You lower the melting point of rock that is already near its melting temperature and you get partial melt. You get a region of rock that is mostly still solid but contains a small fraction of melted material, and that mixed solid plus melt region transmits seismic waves differently from solid rock alone. What Jacobson and Schmant were seeing in the US Array data, the slight slowing of seismic waves near the base of the transition zone was, they argued, consistent with exactly that scenario. Descending rock, rich in ringwoodite, reaching the 660-kilometer boundary, shedding its water as the mineral transformed, that water triggering partial melting in the surrounding rock, and the seismic waves registering the presence of that melt. If they were right, the evidence for water in the mantle transition zone was not resting on a single diamond from a single kimberlite pipe in a single region of Brazil. It was visible from the surface in the way that seismic waves move through the whole planet. The whole transition zone, or at least a substantial portion of it, was behaving in the way you would expect it to behave if it were wet. To read that from the motion of the ground during an earthquake. To translate 500 separate shaking events recorded at hundreds of stations across a continent into a statement about water chemistry at 660 kilometers depth. There is a kind of patience in that work that matches the patience of the Earth itself, a long and careful listening that eventually yields something that sounds simple but is not. The rock is wet, we can tell because of how it sounds. In combination, the diamond result from Pearson's group and the seismic result from Jacobson and Schmant told a story that neither could have told alone. The diamond said, here is an actual sample and it contains water and we can measure it, and the measurement is 1.5% by weight. The seismic work said the behavior of the transition zone across a large area is consistent with a wet zone, with water being released at the base and causing the kind of partial melting you see when hydroxyl-rich rock crosses a phase boundary. Together, they were independent lines of evidence converging on the same conclusion. This is how science earns confidence, not from one dramatic find, however convincing, but from multiple independent approaches that could, in principle, have disagreed with each other, each one looking at the same question through a different window, each one finding the same answer. The diamond looked through one window, the seismic network looked through another, and both windows opened onto the same room. The room is wet. Think for a moment about what it means to detect something at 660 kilometers depth by listening to earthquakes from the surface. The Kola superdeep borehole, drilled in the Kola Peninsula in what was then the Soviet Union, over a period that began in 1970 and continued for decades, is the deepest artificial hole ever made in the Earth's surface. It reached approximately 12 kilometers depth after years of drilling, encountering unexpected heat and unexpected conditions that eventually slowed and then halted the project. 12 kilometers, the distance you might drive to a grocery store in a city with heavy traffic. That is the deepest physical reach humans have ever achieved in the solid Earth, the furthest we have ever literally penetrated the planet's crust with a physical instrument. The transition zone begins at 410 kilometers. It ends at 660 kilometers. The shallowest part of it is more than 30 times deeper than the deepest hole ever drilled. The deepest part is more than 50 times deeper. No drill has come close. No drill could come close with any technology currently imaginable, because the temperatures and pressures at those depths would destroy any physical instrument before it arrived. The kimberlite diamond from Brazil is the only sample that has ever left the transition zone and reached the surface intact. And it did so not through any human engineering, but through a geological accident, a volcanic eruption that fired it upward faster than the pressure could re-equilibrate its contents. And yet the transition zone is not unreachable to human knowledge because the seismic waves reach it, because every earthquake sends energy through the whole planet, and the Earth's response to that energy carries information about what it passed through, and the instruments at the surface can read that information if they are numerous enough and sensitive enough, and the analysis is careful enough. The USA Array's more than 400 stations recorded 500 earthquakes and produced a picture of the deep Earth that no drill could ever have provided. The planets spoke and the seismologists listened. Wadsleyite in the upper part of the transition zone from 410 to 525 kilometers, holding up to 3% of its weight as water. Ringwoodite in the lower part from 525 to 1660 kilometers, holding approximately 1.5% of its weight as water, confirmed by the diamond from Juína. Together, across the full 250-kilometer depth of the transition zone, spread around the entire planet in a layer of rock wrapped around the Earth like the shell of an enormous egg, these two minerals constitute what might reasonably be called a reservoir. Not a reservoir of liquid, not a place where water gathers and moves and sloshes, but a reservoir in the chemical sense, a store, a capacity to hold something and keep it. The numbers that come from trying to calculate how much water is stored in this reservoir are numbers that the mind does not easily accommodate. If the transition zone is hydrated throughout at the concentrations the diamond sample and the laboratory experiments suggest, the total amount of water stored in the rock could equal somewhere between 1 and several times the volume of all the water in all of Earth's surface oceans combined. The Atlantic, the Pacific, the Indian, the Arctic, the Southern Ocean, all of the seas and all of the bays and all of the marginal waters that ring the continents added together and then multiplied. That total volume, perhaps that total volume more than once, may be sitting 400 miles below your feet tonight, pressed into the crystal architecture of rock that has never seen sunlight. It is held there not in pools, not in veins, not in cavities in the rock. It is held there in the atomic structure of the minerals themselves. Every unit cell of a Wadsleyite crystal, that basic repeating module of the mineral's architecture, the smallest unit that contains all the information needed to build the whole crystal, can include hydroxyl groups as part of its structure. Water that is not water. Hydrogen and oxygen bonded not to each other but to the mineral's own framework, dispersed at the atomic scale through the rock, invisible even to the electron microscope unless you are looking for the specific chemical signature. This is what the popular image of an underground ocean gets wrong, and why getting it right makes the actual story more astonishing rather than less. The underground ocean is not hidden somewhere you could theoretically explore if you could only dig deep enough. It is not a cave system on a grand scale, not an aquifer the size of a continent, not a body of water that could be drained or pumped or sailed on. It is woven into the rock. The rock and the water have become each other, in a sense, the water surrendering its identity as a liquid and becoming, for the duration of its stay in the transition zone, an aspect of the mineral itself. And it arrived there through a process that has been running for as long as the Earth has had oceans on its surface and plates moving across its mantle. That process, how the surface water found its way into the deep rock, and how it will eventually find its way back, is the next part of the story, the part that connects the hidden ocean to the one you know. But rest now for a moment with the names. Ted Ringwood, working at a high-pressure apparatus in Canberra, predicting minerals he had never seen in nature, describing crystal structures that existed only under conditions no laboratory could fully reproduce but could approach, writing the vocabulary of the deep earth before anyone had opened the book. Arthur David Wadsley, arranging atoms in his mind, building a crystallographer's understanding of how minerals hold their structures, contributing foundations that others would build on for decades. both of them gone before the diamond from Mato Grosso arrived to confirm what their framework had predicted. And in meteorites, fragments of ancient violence falling from the sky, the mineral was already there, preserved from shocks that happened billions of years ago on bodies that no longer exist, carrying the chemical fingerprint of extreme pressure, waiting to be recognized. The first ringwoodite on Earth came from above, not from below. It came from the history of the solar system rather than from the history of this planet. Then the seismologists, listening to earthquakes with hundreds of instruments spread across a continent, translating the motion of the ground into a picture of what lies beneath, detecting in the slight slowing of sound through rock the presence of partial melt, working backward from the melt to the water, from the water to the mineral, building a case from vibration alone. The transition zone does not announce itself. It sits in the dark at temperatures and pressures no human being will ever experience directly, doing what it has done for billions of years, holding the water that passed into it, keeping it in the lattice of its minerals, waiting for the conditions to change. The 410-kilometer boundary is not visible from the surface. The 660-kilometer boundary is not marked by any feature on the landscape above it. The whole 250-kilometer zone passes beneath cities and oceans and deserts and ice sheets without the faintest trace on the surface that would indicate what lies below. The ground underfoot gives no indication that any of this exists, and yet it does exist. The seismic waves say so, the diamond says so, the laboratory apparatus says so. The names given to the minerals by two men who worked in the southern hemisphere in the decades after the Second World War say so, names that now attach to things that are real and deep and full of water and as far from any ocean you have ever seen as anything the planet contains. Sleep carries you through the night the way the wave carries the mineral through the rock, slowly, inevitably, without effort on your part. The transition zone will be there in the morning, and the wadsleyite will still be holding its water, and the ringwoodite at its lower boundary will still be pressing against the edge of what it can contain, and the seismic waves from some distant earthquake will be moving through it right now, carrying their information through the darkness up toward the surface where an instrument is waiting to listen. And here, at the deepest edge of the transition zone, something happens that is as close to a transformation as anything the planet performs. Ringwoodite, that mineral with its spinel structure and its locked hydroxyl groups and its deep blue hue, in the laboratory samples held under glass, can only exist within a certain range of pressure. It is stable where it is, pressed on all sides by the weight of the rock above it, shaped by the conditions that prevail between roughly 525 kilometers and 660 kilometers down. It has been shaped by those conditions for as long as the Earth has been cycling material through its interior, which is to say for a very long time, a span of years that makes any human measure feel like the blink of an eye in a creature that never sleeps. But the boundary at 660 kilometers is real, and it is not negotiable. Below that line, the pressure changes in a way that the ringwoodite crystal cannot accommodate. The atomic structure that made it stable above the boundary, the arrangement that allowed it to take in hydroxyl groups and hold them in the lattice, like water gathered in the cupped hands of the rock, cannot persist below it. The 660-kilometer discontinuity, the deeper of the two seismic boundaries that define the transition zone, is not just a number, it is a threshold. And when ringwoodite crosses that threshold, carried downward by a sinking slab of oceanic plate, or drawn into the slow, convective descent of the mantle itself, it cannot remain what it was. The word that researchers use for what happens is not dramatic, it is quiet, almost biological in its imagery. Ringwoodite sweats. Imagine holding a sponge saturated with water, and then squeezing it, not gently, but with the kind of force that changes the shape of the sponge itself, that restructures it from the inside, that reorganizes its molecules into a new configuration that simply does not have room for the water that was there before. The water is expelled. It has nowhere to go but out. What emerges from the sponge is no longer the same thing that went in, and the water that was held inside, that was part of the structure, in a sense that went beyond mere containment, is now free, released into the surrounding medium, changed in its state, if not in its chemistry. What ringwoodite releases at the 660-kilometer boundary is not liquid water in the way you would recognize it. It is water in the form of hydroxyl, freed from the crystal lattice as the mineral restructures itself into the phases stable in the lower mantle. The lower mantle is not the transition zone. The lower mantle is a different regime, governed by different pressures and different mineralogy, and the minerals that are stable there do not have the same capacity to hold water that wadsleyite and ringwoodite have. When the material crosses the discontinuity, when it descends past that line, the water that was bonded into the structure must go somewhere, and where it goes is into the surrounding rock as fluid, briefly, a flash of released water at the base of the transition zone, almost immediately recaptured or incorporated, but undeniably there, undeniably present, in a form that seismic waves can detect, because water changes the behavior of rock under certain conditions, lowers its melting point, alters the way waves move through it. This is precisely what Stephen Jacobson at Northwestern University and Brandon Schmant at the University of New Mexico were looking at when they published their own study in Science in the same year that Graham Pearson's team published in Nature. Their tool was not a diamond. Their tool was the Earth itself, which had been generating earthquakes for as long as it had been geologically active, each earthquake sending seismic waves radiating outward through the interior in all directions, waves that carry information about the properties of the material they pass through, the way that light carries information about what it encounters. They used data from more than 500 earthquakes recorded by the US Array Network, which is an instrument system spanning the continental United States, a grid of seismometers dense enough to read the interior of the planet with a resolution that earlier generations of geophysicists could not have imagined. What they were looking for was evidence of melt, partial melting, which is what happens when rock reaches a temperature above the point at which some of its components liquefy, even if the rock as a whole remains solid, changes the seismic properties of a zone. Waves slow down in partially molten rock. They behave differently. And at the base of the transition zone, right at the 660-kilometer discontinuity, Jacobson and Schmant found the signature they were looking for: signs of partial melting, rock that was behaving seismically the way rock behaves when it contains some component that is not fully solid. The interpretation, consistent with the laboratory experiments they also ran under high-pressure conditions, was that this partial melting was being caused by water. Water released from ringwoodite as it crossed into the lower mantle. Water that had been locked into the crystal structure through the long descent and was now at the deepest edge of the zone where it had been held, being expelled and briefly changing the nature of the rock around it. Two studies, two methods, one in the physics of a tiny mineral grain and one in the seismology of a whole planet, arriving at the same conclusion from opposite directions. The water is there, not as ocean, not as river or lake or any body you have ever imagined, but it is there, moving in ways that are planetary in scale and geological in time, as real as anything science has found inside the Earth. And the question that follows from this, the question that opens naturally from the idea of water being expelled at the base of the transition zone, is where it goes and where it came from. Because those two questions, where the deep water comes from and where it goes, are the same question approached from different directions. And together they describe something that takes the simple image of the discovery, water inside a diamond inside the Earth, and expands it into something planetary. Something that connects the deepest interior of the planet to the surface you live on, connects the ocean you can see to the ocean you cannot, through a cycle so slow it makes the seasons feel instantaneous. The water that is locked inside ringwoodite and wadsleyite in the transition zone did not appear there spontaneously. The mantle was not born with this water already distributed evenly through its minerals. The water got into the deep interior by being carried there, and the mechanism by which it was carried is one of the defining processes of Earth's geology, the process that shapes the surface, that builds mountain ranges and opens ocean basins and triggers the earthquakes and volcanoes that remind us periodically that the planet beneath us is not inert. Subduction is the word. It sounds technical, almost bureaucratic, but what it describes is one of the most consequential things that happens on this planet. The Earth's outer shell, the lithosphere, is broken into plates. Some of those plates are oceanic plates, underlain by the dense, heavy basaltic rock of the ocean floor. And oceanic plates, unlike continental plates, are subject to a kind of fate that the thicker, lighter continental plates mostly avoid. They sink. At the margins where an oceanic plate meets another plate and the forces of the deep mantle push them together, the oceanic plate dives beneath the other and descends into the mantle. This is subduction. It is a slow process, measured in centimeters per year, but it is relentless, and it has been happening for hundreds of millions of years, and the cumulative effect of all that slow descent is that enormous quantities of material from the ocean floor have been carried down into the mantle over geological time. What the ocean floor carries with it into this descent is not just rock. The ocean floor is saturated. Seawater infiltrates the basalt of the ocean crust through cracks and fractures and chemical reactions, and the minerals that form in response to this infiltration are hydrated minerals, minerals with water chemically bonded into their structure. Serpentine is one of them, a mineral that forms when the iron and magnesium silicates of the ocean floor react with seawater, and serpentine holds water in its crystal structure with considerable tenacity. There are others too, a family of hydrated minerals that form in the altered rock of the oceanic plate, each holding water in a different way, each releasing it at a different depth and temperature as the plate descends and the conditions change. At shallow depths, some of this water is released early. The fluids that rise from the shallow parts of a subducting plate feed the volcanoes that form in long chains above subduction zones, the arcs of volcanoes that circle the Pacific, the chains of islands and coastal peaks that mark the places where plates are diving beneath the surface. This is why arc volcanoes are so wet, so rich in steam and water vapor compared to the volcanoes that form over hotspots in the middle of plates. The water released from the shallow subducting slab rises into the overlying mantle wedge, lowers its melting point, generates magma, and that magma rises to the surface as volcanic eruption. The water returns. It has made part of its circuit. But not all of the water in the descending plate is released at shallow depths. Some of the hydrated minerals are more tenacious. They hold their water deeper through higher temperatures and greater pressures, and they carry it down past the depths where most of the volcanic water is released, down through the transition from the upper mantle into the transition zone, down to the depths where the mineralogy changes and the pressures are high enough to stabilize ringwoodite and wadsleyite. And when the material of the descending slab reaches those depths, when the temperature and pressure conditions cross the thresholds that stabilize the high-pressure phases, some of the water that was carried down in the hydrated minerals can be taken up by wadsleyite and ringwoodite, incorporated into their crystal structures stored in the deep reservoir. This is the descending arm of the deep water cycle. Surface water bound into the minerals of the ocean floor, carried downward by the slow, relentless sinking of tectonic plates, accumulated over millions and millions of years in the transition zone where the mineralogy can hold it. The ocean, in this sense, is not separate from the deep interior. It is connected to it, feeding it slowly, delivering water to a reservoir that has been accumulating its contents since the Earth was young. And the water returns. not quickly, not in any time frame that a human civilization could observe directly. But it returns through the same volcanic processes that have always exchanged material between the mantle and the surface, through the upwelling of mantle material at the mid-ocean ridges and hotspots, through the arc volcanoes above subduction zones, through the slow outgassing of the interior over geological time. The water that sank into the mantle transition zone 200 million years ago or 500 million years ago may be part of the ocean today. It may have passed through a volcano, been released as steam, rained down into a river, and found its way back to the sea. The cycle is not hypothetical. It is the mechanism by which the Earth manages its water budget over geological time, balancing what goes down with what comes up, maintaining the surface oceans through a replenishment that operates on timescales so vast that no human instrument has yet managed to follow a single water molecule all the way through it. What this means for the scale of the deep reservoir is something that researchers estimate with appropriate caution, because the estimate depends on assumptions that are not yet fully settled. The ringwoodite sample from the diamond in Juína holds roughly 1.5% water by weight. Wadsleyite in laboratory experiments can hold up to about 3%. If those concentrations are representative of the transition zone as a whole, if the water-bearing minerals are distributed throughout the full 250-kilometer depth of the transition zone and not just in isolated pockets or localized regions, then the amount of water stored in the deep rock is very large. One estimate, credible and peer-reviewed but acknowledged to be uncertain, is that the transition zone holds an amount of water comparable to the volume of all the surface oceans combined. Some estimates go higher, suggesting several times the volume of the surface oceans. Other estimates are more conservative. The uncertainty is real, and it is worth dwelling on for a moment, because the numbers that circulate in popular accounts of this discovery are often stated with more confidence than the science itself warrants. Graham Pearson's team found one sample, one diamond, one inclusion of ringwoodite with one measurement of water content. That measurement is real. It is the first direct physical evidence of water in ringwoodite from Earth's own interior. But one sample does not tell you how uniformly the water is distributed through the entire transition zone, which is a shell of rock encircling the entire planet at depths between 410 and 660 kilometers. The transition zone contains an enormous volume of material. Whether all of it, or most of it, or only part of it, is as water-rich as the sample from the Brazilian diamond is a question that seismology can address statistically by reading the behavior of waves across the whole zone, but not yet definitively settle. The honest answer, the one that reflects where the science stands, is this. There is very likely a large quantity of water stored in the transition zone, far more than anyone had suspected before the era of diamond inclusion studies and high-pressure laboratory experiments and the US Array seismic network. The estimate of 1 to several oceans' worth is a credible scientific estimate held with appropriate uncertainty, not a settled census. It may be revised upward or downward as more samples are studied and as seismic methods improve. What is not in doubt is that the amount is significant, that it changes the way we understand the water budget of the planet, and that the discovery of the ringwoodite inclusion in the Juína diamond was the moment when that significance became undeniable, when a single tiny crystal turned a theoretical prediction into measured physical reality. There is something else worth saying about that water, about what it means that it is there in the quantities suggested, bonded into the rock and cycling slowly through the deep interior. It means that the Earth is not quite the planet it appears to be from the outside. From the surface, from the vantage point of a human life or even a human civilization, the planet seems to be divided neatly. The surface, with its oceans and rivers and rain, And then the deep interior, solid and dry and hot and remote, a place of rock and iron with no connection to the water above. The diamond changes that picture. The seismology changes it. The transition zone, those 250 kilometers of high-pressure mineralogy deep beneath the continents and ocean floors, is not a dry reservoir. It is wet. It is connected to the surface through the long, slow exchange of subduction and volcanism. And it has been connected this way probably for most of the history of the planet. This means that when you look at the ocean, you are looking at one part of a system that extends much further than the visible surface. The water in the Pacific, the water in the Atlantic, the water in the deep ocean trenches, the water in the clouds and in the rivers and in the glaciers and in the soil is not isolated from the water below. It is the surface expression of a planetary water budget that includes the deep interior, a budget that has been managed by the cycle of plate tectonics for hundreds of millions of years. The same cycle that moves the continents and generates earthquakes and builds mountain ranges and does all the things that make the surface of the Earth the complex, changing, geologically active place it is. Water is part of that cycle. Water has always been part of it. It was simply below the reach of any human instrument until a team at the University of Alberta noticed something in a brown diamond bought for around $20. Imagine standing at the edge of an ocean, which you may have done once, or many times, or perhaps only in memory or imagination. You are looking at water. You know what water is, you know what it feels like and what it looks like and what it does. Now imagine that beneath the sand under your feet, beneath the bedrock under that, beneath the tens of kilometers of crust and the hundreds of kilometers of upper mantle at a depth 400 miles or more below the surface, there is more water. Not in a sea you could sail on, not in a cavern or a lake or any space you could enter. It is in the rock. It is in the atomic structure of the minerals held there by the pressure of the planet itself, part of the crystal lattice the way hydrogen is part of everything that burns. It is water that has stopped being water in any form you would recognize, dissolved into stone, bonded into the architecture of the deep earth, and it has been there, probably, for longer than life has existed on this planet. And it is connected to the ocean you are standing beside. The same water cycle that moves water through the atmosphere and into rivers and back to the sea has a deeper counterpart, slower by orders of magnitude, operating through the mechanism of tectonic plates rather than the mechanism of weather. The surface ocean loses some of its water to the deep over millions of years, carried down by the rock of the ocean floor as it sinks at subduction zones. The deep reservoir returns some of its water to the surface over millions of years, carried up by rising magma and outgassed at volcanoes and mid-ocean ridges. The system is in balance, roughly, over the long term, the way a very slow pendulum is in balance, swinging so slowly that it appears still. The brown diamond from Juína, the one that sat in a rock collection for a while, undistinguished, commercially worthless, its extraordinary interior, invisible to any casual inspection, the one that Graham Pearson's team bought for around $20 while looking for something else entirely. That diamond is the evidence that this balance exists, that this deep cycle is real, that the planet is doing something with its water that no human civilization was aware of until very recently. The ringwoodite inclusion, smaller than the width of a human hair, nearly destroyed during analysis, holding 1.5% water by weight, in a crystal structure no larger than a dust mote, carries a whole planetary story inside it. The diamond did not intend to tell that story. It was simply a piece of the deep earth, enclosed in carbon at a depth where the pressures are unimaginable, carried to the surface by a kimberlite eruption, the fast and violent ascent of deep magma that is the only mechanism that could have delivered it intact and then found, cut, examined under instruments of extraordinary precision, and revealed. The story was always there. It waited, sealed inside the hardest natural substance on Earth, at pressures that locked the ringwoodite in place and prevented it from reverting to the olivine it would have become if it had traveled up more slowly. It waited until the instruments existed to read it. It waited until someone was curious enough to look. Ted Ringwood, the Australian geophysicist whose name attaches to the mineral, predicted that such high-pressure phases should exist in the mantle long before anyone held a terrestrial sample. He worked out the thermodynamics, the phase diagrams, the conditions under which olivine should transform into the denser structures his calculations required. He was working in the mid-20th century with the mathematics of mineral physics, but without any direct sample from the deep earth to confirm his predictions. He predicted ringwoodite. He predicted the transition zone. He did not live to see the Brazilian diamond, but the mineral that carries his name was, in its existence, a vindication of his lifetime of theoretical work. Arthur David Wadsley, the British-Australian mineralogist whose name attaches to wadsleyite, the shallower cousin that holds even more water, up to about 3% by weight in laboratory conditions, was working in the same era, identifying mineral structures, characterizing the phases that high-pressure experiments were beginning to reveal. These men were working at the edge of what could be known at the time, extrapolating from laboratory experiments and theoretical calculations into the interior of a planet that was, and remains, largely inaccessible to direct sampling. They gave their names to minerals that exist hundreds of kilometers below the surface of the Earth, and those minerals, as it turns out, are hiding water in quantities that dwarf every ocean on the surface. There is something in that fact that goes beyond the chemistry and the seismology, something about the nature of discovery itself, about the way that understanding arrives not all at once but in pieces, each piece enabling the next, each confirmed prediction opening a new set of questions that require a new generation of instruments and methods and curiosity to answer. Ringwood predicts the mineral. The mineral is found in meteorites, in shocked rock from ancient cosmic impacts where the pressures briefly matched what the deep Earth produces over long spans of time. Decades pass, the tools improve. A diamond from Brazil carries a microscopic fragment of that mineral up from 400 miles down. A team at the University of Alberta buys the diamond for about $20. The inclusion is nearly destroyed, the water content is measured, and the surface of human knowledge shifts just slightly in the way that real discoveries shift it. Not by overturning everything that came before, but by filling in a space that had been empty, by confirming something that was suspected but unproven, and by revealing that the space around the confirmed thing is even larger and more complex than anyone had thought. The water in the transition zone, however much of it there is, whether closer to one ocean's worth or several, whether more concentrated in certain regions or more evenly distributed, whether rising and falling in quantity over the deep cycles of planetary history, is not going anywhere on any human timescale. It is not about to be released, is not threatening to flood anything, is not going to change the level of the surface oceans in any period that a human civilization would recognize as meaningful time. The deep water cycle operates on timescales of tens to hundreds of millions of years. A subducting plate carries its water down over millions of years. The water works its way through the mineralogy of the descending slab over millions more. It arrives in the transition zone, if it arrives there, after a journey of geological time. It returns to the surface through volcanism and upwelling on timescales equally vast. Human civilization, from its earliest settlements to whatever it might become in the distant future, is a brief event against these rhythms. The planet's water budget balances over timescales that are entirely indifferent to the history of any species. But knowing that the cycle exists, knowing that the deep reservoir is there, knowing that the planet is managing its water in ways that extend far below any drill or any submarine or any instrument humans have yet placed in the ground, that knowledge changes something about the way the Earth can be understood. It means that the surface and the interior are not separate systems that happen to share a planet. They are connected. They exchange material and energy across boundaries that seem impossibly remote, but are, in the geological sense, actively engaged with the surface world. The rain that falls tonight, wherever you are listening from, is part of a water cycle that you know. It evaporates, rises, condenses, falls again, drains to a river, reaches the sea. That is the cycle that every schoolchild learns. What the ringwoodite in the Juína diamond tells us is that beneath that familiar cycle, operating on timescales that no human will ever directly observe, there is another one, deeper, slower, stranger, and in terms of the total volume of water it manages, almost certainly larger. The mantle transition zone does not announce itself. It leaves no signature on the surface visible to the eye, no geological feature you could point to and say, there. That is where the transition zone is, that ridge, or that valley, or that particular quality of the light. It is defined entirely by what instruments read and what mathematics predicts, and what a diamond occasionally carries up from its depths. It is known indirectly, understood inferentially, confirmed by the convergence of methods that no single scientist or discipline could have assembled alone. Seismology, mineral physics, diamond geology, the patience to examine a commercially worthless brown stone from a collection in Brazil and notice, in the microscopic inclusion nearly lost during analysis, a piece of the deep earth that no one had held before. This is how the planet gives up its secrets, not through grand revelations or dramatic surface features, but through small and difficult and painstaking work at the boundary of what is possible to measure, through a diamond that nobody wanted to buy, through instruments listening to 500 earthquakes, through the accumulated theoretical work of researchers working decades before the tools existed to confirm what they predicted. The ocean beneath the Earth is not a discovery that arrived in one moment. It is a discovery that assembled itself from fragments over decades, each fragment dependent on the ones before it, each one opening a door that the next generation of instruments would walk through. You are very far from Juína, Mato Grosso, Brazil tonight, in all likelihood. You are very far from the University of Alberta. You are far from the laboratories where ringwoodite sits in a high-pressure cell and is measured, far from the seismic stations of the US array reading the slow reports of distant earthquakes, far from the kimberlite pipe through which that small, brown diamond was carried to the surface by volcanic violence millions of years ago. You are at the surface of the planet where the water is the kind you know, liquid and familiar and falling occasionally from the sky or moving in rivers or gathered in the ocean if you are close enough to hear it. But the transition zone is beneath you. It is beneath wherever you are reading or listening from, beneath the crust and the upper mantle, sitting in the dark at depths that no human technology has approached, holding its water in the crystal lattices of minerals named after two men who never held a sample of what they predicted. The 410-kilometer boundary is real. The 660-kilometer boundary is real. The water between them bonded into the structure of wadsleyite and ringwoodite, sweating out at the lower edge as material crosses into the lower mantle where the structure can no longer hold it, cycling slowly upward over geological time through the same volcanic processes that have shaped the surface for billions of years. All of it is real. The diamond confirmed it. The seismology confirmed it. The numbers, uncertain as they are in their upper and lower bounds, point toward a quantity of water stored in the deep rock that exceeds, possibly several times over, everything in every ocean, every lake, every river, every cloud you have ever seen. And none of it is liquid. None of it is water in the way you understand water. It is water that has become something else, that has dissolved into the fabric of the rock itself, that is present not as a substance you could collect or drink or sail upon, but as a chemistry, a state of the mineral, a property of the crystal lattice at depths where the pressure is measured in hundreds of thousands of times the pressure at the surface. The popular image of a vast underground sea, a subterranean ocean with waves and currents and darkness and the smell of salt water, is not what is there. What is there is stranger than that, and in its strangeness, more wonderful. Rock that is water. A mineral that is an ocean. A crystal structure that is a reservoir. A diamond that is a message from 400 miles below the ground, delivered by the violence of a volcanic eruption, bought for around $20, nearly destroyed in the analysis, and carrying inside it, in a fragment smaller than the width of a human hair, the proof that the planet is wetter than anyone knew. The ringwoodite is still down there tonight, in whatever formations and deposits and descending slabs hold it through the transition zone, pressing against the limit of what its structure can contain. The wadsleyite above it, in the upper part of the transition zone, is still holding its water, perhaps a higher concentration still, in the lattice of its crystals. The seismic waves from earthquakes that happen today, somewhere in the long seismically active belts of the planet, are moving through the transition zone right now, carrying their information upward through the rock toward the instruments at the surface, adding incrementally to what the planet is willing to tell us about itself. The deep water cycle continues as it has continued for hundreds of millions of years, plates descending with their cargo of surface water, volcanic systems returning some of it over long spans of time, the interior and the surface in slow exchange, indifferent to any observation but entirely available to it. If you are somewhere near water tonight, near an ocean or a lake or a river, or if it is raining where you are, or if you can only imagine water because the air is dry and the sky is clear and the nearest river is far away, it is the same water. The same hydrogen and oxygen that falls through your atmosphere and moves through your rivers and fills your oceans is the same element, in its same chemistry, that is locked into the crystal architecture of ringwoodite 400 miles below the surface. The deep and the surface are part of one system. They always have been. The discovery made by Graham Pearson's team, published in Nature in 2014, confirmed something that the planet had been doing quietly for its entire geological life, long before there was anyone to discover it, long before there was a surface ocean to compare it to, long before there was a word for water, or a word for ocean, or a word for earth. The hidden ocean is not hidden because it is secret. It is hidden because it is inside the rock, and the rock is inside the planet, and the planet is very large and very deep and has been keeping this particular fact about itself to itself for a very long time, until a small brown diamond from Juína, Mato Grosso, Brazil, decided in its geologically passive and entirely involuntary way to say otherwise. If you feel moved to share where you are listening from tonight, I would genuinely like to know, somewhere in the world, at this hour, you are lying in the dark above a planet that is wetter than it looks, above a transition zone that has been holding its water in silence for longer than any ocean has existed, above a deep cycle that has no knowledge of you and no interest in being observed, and yet which is, in some quiet fundamental way, connected to the water in the glass on your nightstand, the rain on the window, the sea you may have visited once or may be hearing right now. The comments are there, and I read them. There are more stories here of the same slow and careful kind, waiting for whenever you want them. You have done enough for one night. Let the transition zone do what it does. Let the ringwoodite hold what it holds. Let the seismic waves move through the dark in their slow and informative arcs from one side of the planet to the other, and let whatever distance they carry, whatever information they deliver to the instruments waiting at the surface, be enough for now. History will still be here in the morning. For now, rest.